Welcome back, class. Today we're going to continue our exploration of linear equations. And we're going to talk about first LU factorization, and then we're going to talk about how we can find matrix inverses and how we can use them to solve problems a little bit faster. So just as a review, we started our conversation about linear algebra by talking about how we can solve linear algebraic problems. Particularly last time we talked about determinants, using determinants within Cramer's rule to solve for that row of variables. And then we talked about Gaussian elimination and then special cases such as partial pivoting and tridiagonal systems. As you remember, we spent a lot of time talking about forward elimination and back substitution. These ideas are going to come in handy today as we talk about LU factorization and then later talk about matrix inverses. So today's objectives are to introduce you to LU factorization, which is going to be a way to essentially save the information from a Gaussian elimination process. We'll briefly touch on the Cholesky method, and then we'll talk about how we can use that LU factorization in terms of matrices inverses, stimuli response characteristics, and then finally we'll talk about matrix norms, condition numbers, and estimating the precision of our solution to round out our conversation, or our discussion of linear algebra. After today's lesson, we'll move on away from sets of simultaneous linear equations to sets of non-linear simultaneous equations. But first, let's talk about LU factorization. If you remember, in Gaussian elimination, we had to first do forward elimination and then back substitution. And really the hard part was that forward elimination, where we took these pieces and we moved, we took this matrix and we went in and calculated that upper triangular matrix. If you remember, that took a lot of the time. The question becomes, if I were to take essentially the same matrix, all the same A's, and then just switch what was equal to on the right side of the equation. So you can think about that in, let's say I have the same reaction chamber setup and I'm just changing maybe the size of reactors, for example. I would have to go back and redo all of that work, right? All of that hard work of doing that forward elimination. But many of the same steps are essentially going to be the same, right? I have to go through each of these and do that, multiply by that factor A21 over A11, and do all that subtraction, right? And I would have to go back and do all of that again for the identical matrix. So this raises a question. Can we save the work from, of doing that factoring when my B vector is changed? So when I move from, say, B1, B1, B2, B3 to C1, C2, C3. And the answer is yes, we can through what's called factorization, or else we wouldn't really be talking about it, right? And so this is going to be called LU factorization. Let's just really briefly remind ourselves how Gaussian elimination is going to work, and then we'll see where this LU factorization comes in. So remember, we have, say, this matrix A times a vector B, this matrix A times the vector X, and that's going to be equal to our vector B. And we want to do the forward elimination on this matrix so that we have this upper triangular matrix where everything below that diagonal is a set of zeros. And in doing so, we convert A into a matrix U, so for the upper triangular, and we end up transforming B into D. And so we can write this out in this form where we've transformed U times X minus D equal to 0. So we can sort of shuffle that back and forth. Now, we want to see how is there some sort of matrix that will enable us to transform this bottom equation into, this bottom left equation into the bottom right equation. So is there some sort of matrix that I can multiply this by? So some sort of matrix that then gives us that set of equations. And it is, so we're going to call that L. So we're going to call this matrix L. And so we want to find, we're going to, over the course of LU factorization, we want to find what this L is, such that when I multiply it through by the U X minus D, I get back that starting equation. And so if you multiply that through, what we'll see is this would give us LU times X. So LU times X. We want that to equal A times X. So L times U must be equal to A. And similarly, if I take L times D, we want that to equal to B. So we have the second relationship that we want to have. So really what we're talking about is we want to find some factor L that when I multiply it by U, I get A. In the end, this is then going to enable us to come in and solve very easily for this bottom factor. Right? The whole idea is to figure out how to get this change relatively easily. Is going to come in when we take this bottom piece, where we take L times D equal to B. We can readily find D. Once we know D, we can readily find X. So in essence, what we're going to do is a two-step process, where our first step is we're going to factor A into L and U. Then we're going to use these factors L and U to back substitute into X. So the first time we do this process, we're not going to gain anything, right? So the first time we decompose A into L and U, we get no speed up because we're having to do that for Gaussian elimination anyways. The key step is going to come when we want to back substitute into X to get that we get the speed up when we start replacing that right-hand side. So sort of schematically, what we're going to do is we're going to take A, factor it into L and U. We can then take L, multiply that by the vector D is going to give us B. So right, we can use, we'll use forward substitution in order to get that D vector. And then we can take the equation U X equals D is going to give us X. So let's put this into practice. We're going to take the same steps that we did for Gaussian elimination, but we're going to store the information in slightly different forms. We're going to take an example matrix A, multiply it by X, and set that equal to B. Or we can represent it slightly differently if I pull this B over onto the other side of the equation. So as we go through our Gaussian elimination, we're going to populate this U matrix just like we had previously done. Remember, we're going to populate both this U matrix, and we're going to get slightly different coefficients on the right-hand side occupying D. In order to get U22, and to get this sort of second row having a 0 in the first column, we needed to find a factor that we could multiply the top row by in order to result in a 0 when we subtracted it off from that A21. So that Gaussian elimination factor, F for factor, to eliminate row 2, column 1, is the ratio of A21 over A11. This is, if I take this factor, multiply F21 across that whole top row and subtract it from the second row, I'm necessarily going to get 0 in that U21 column. If I change B, I still need that exact same factor, right? If I change this B vector, right, if I were to change any of these values, that would not change what happens here. So what I'm going to do is I'm going to take this factor and I'm going to put it in a matrix called L. And that's going to sit in the 2, 1 spot. I can then consider what I would need to multiply that top row by. So what would I need to multiply the top row by if I wanted to get a 0 in this A31 spot? Well, that's the factor A31. And it's going to be sort of similar to the factor 21, right? It's the ratio between the value in A31 and A11. Once again, so that when I multiply and subtract, I end up having a 0 in that first column. So once again, I'm going to take that value and I'm going to put it in its spot in this L matrix. So now we've taken care of that first 0, we've taken care of that second 0. We now want to tackle that third 0. Here, my factor A32 is not equal to A32 over A22, right? If you notice here, I have these apostrophes. That's because when I'm building that upper diagonal matrix, this U22 is now different. And as I'm building that matrix, you know, the temporary A32 is also, you know, not equal to this, right? They're not equal because we've already gone through one round of elimination. Therefore, I'm going to refer to those as prime. So those are that next value that's coming in. So I'm going to take that prime value and I'm going to put it into the spot into that matrix set where it goes. I then want to take this and I want to form a full matrix. But what goes in this upper diagonal half? Well, let's remember that I need L times U to equal A. The only way that this can be true, is if the diagonal elements are 1s and the upper elements are 2s. This is going to keep the elements, those upper U elements, from coming through in the A matrix while maintaining you know, the correct number along that diagonal. So in our factoring step, we're going to take the Gaussian elimination factors that we used to calculate that upper triangular matrix, and we're just going to store them in this L matrix, in this lower triangular piece. We're going to get 1s along the diagonal and 0s in the upper right-hand corner. So after we factored L and U to get our L matrix with the F's, our U matrix with the A's and the A primes, we need to start thinking about getting our D and our B. So we can remember that D, which we're going to use for solving this out, remember U x equals D. To get this D, we can look at this L matrix, right? I have a diagonal I have this diagonal or a lower diagonal matrix. We've got these D1, D2s, D3s that we're interested in solving for. And so you can see immediately that I know what D1 is because I have I've got zeros in the second and third columns, right? So I could do forward substitution where I first solve for D1, then take it and use that information in the second row to solve for D2, then I can take that information to solve for D3. Because we have this nice forward substitution, we have a very, we have a straightforward way of equation for solving for D1. Right, this way, I don't need to go through all that pain of keeping track of all the D's as I'm doing my Gaussian elimination. I can do LU factorization, and then I get this nice sort of more straightforward equation for D. So let's get into it. Let's now move on. So we can do our factoring. We can then do forward elimination to get D, and then we're ready to go back in order to get our X's and B's. So we have L, we have D using this forward elimination. What these D's are going to give us is an easy way to do back substitution. Remember, we have this nice set of U's. We're then going to use the fact that U times X minus D is 0, or put sort of in a mathematical matrix form. We can have our A's times X equals the D's that we solved for using L. Right, and now it's just a back substitution problem. So once we have L and once we have U, we first do a forward substitution to get D, and then we do a back substitution to get our X's. This is going to help us because now, if I wanted to change this B matrix, I only need to do the forward substitution part to get my D, and then back substitution part to get my X, right? Much easier than going through all the Gaussian elimination. I can just do forward substitution, back substitution. I don't need to do any more elimination. Here I have a matrix, A, a vector X, and a vector B. And I want to perform LU factorization on this matrix. The first thing that I'm going to do is I'm going to start writing out L and a U. The nice thing about LU factorization is I get a lot of freebies in solving these problems, right? We know that the U matrix has these three, in a 3x3 matrix, has this lower triangle of zeros, and the L matrix has diagonal of 1s and the upper matrix of 0s. Okay, so automatically we're off to a good start. So this U matrix, right, is going to be the matrix that we get after Gaussian elimination. And in Gaussian elimination, we get to keep the first row. So without doing any math, I've already solved for the vast majority of the elements in my system. So I'm only looking for 3 spots here and 3 spots there. So in order to solve for what those 2 spaces on the U's are, we want to take these two matrices elements, so the first row and the second row. And we want to figure out, what do I need to multiply this by? So we'll call this factor 2, 1, such that I get to eliminate that row. And remember, F21 is going to be equal to 0.1 over 3, where this is element A21, and that 3 is element A11. And this is going to come out to be 0.0333, repeating. I'm not going to just write out all the zeros, but you get this picture. When I multiply this out times that top row, so we'll call this top row, we get 0.0333 times 3, negative 0.1, negative 0.2. This is going to be equal to 0.1, negative 0.0033, and then that last element is negative 0.0066. Once again, we can take this out as far as we want. So now I'm going to take that top line, remove that, and then I can write out those element pieces. And then I can subtract one off from the other. So of course, when I subtract this off, these first 2, one from the other, I get 0. If I subtract 0.0033 from 7, we end up getting 7.0033. And then if I subtract this one off from that one, I get, I'm going to need more space, 0.2 933. Okay, so we've already filled in our U matrix, and then we get to take this guy and put him in our L matrix. Right? Good. So we've got that first, the first row of the U matrix, the second row of the U matrix. We have the first row of the L matrix, the second row of the L matrix. Now it's time to work on the third row. I've cleared the screen and rewrote out row 1 at the top and then row 2. The first thing that we need to do to get rid of this 0.03 is to find that factor 3(1), which remember is 0.3 over 3, which should be 0.1. We can take that 0.1, because this is going to be our factor, and we can just plop that right into our L matrix. I can take that 0.1 from the factor and multiply it through that top row. When I do, I'm going to get 0.3, negative 0.01, and negative 0.02. I can take this through and subtract this row across. That will give me 0, negative 0.19, and 10.02. I can't go and put this into the matrix because we still have this negative 0.19. I have to eliminate the 0.19 before I can put it into that U matrix. So let me clear up some space and we can come back and talk about how we can do that. Now I'm ready to look at this third row. I need to get rid of this 0.19, and the only bit of information that I have left is coming from that second row. So I can write out those two numbers again to sort of help us through here. And we can see that we're going to get our factor to eliminate that from the ratio of negative 0.19 and 7.0033. When I do this this division out, we get negative 0.0271. I have my factor. I can put it in my L matrix, negative 0.0271. My L matrix is done. This is great, but I still need to finish out that last slot for the U's. I can take that factor negative 0.0271, multiply it through that top row, we get negative 0.19, and then 0.008. So now I'm ready to subtract one off from another. I can go through, change all my signs. I get 0, 0, and 10.028. Right? I can now, I have the right number of zeros in my row. I can take that, put that in my matrix, in my U matrix, and we get 10.028. All right, my L matrix is filled out, my U matrix is filled out. I've completely factored this all the way through. I encourage you to go in and check for yourself by taking U times L and making sure that you get back A, which you should. Now that we've completed LU factorization by hand, we can start thinking about using MATLAB functions to generate L and U. This is done so commonly in linear algebra that MATLAB has a built-in function called LU that will do LU factorization for us. What we do is we take LU is going to return two values, L and U. So if we want both of them, we can use an open bracket, whatever variable we want to store L in, maybe capital L, comma, whatever variable we want to store U in, maybe capital U, close the bracket, and then we use the LU function to do our functionalization. Once we get L's and U's, we're now ready to solve our problem. Let's go back and just say we're still working on A times X is equal to B. We can first solve, in order to solve for what X is, we can first use the equation D equals L back division B to solve for our different D's. And then we can use MATLAB to solve this equation, which is that U value times X equal to D's. And we can use back division to solve for that too. So X equals U back division D. This is going to give us X for any variable that we can put in for D relatively easily without having to go through and doing the whole Gaussian elimination again. Before I move on, I just want to note that the function LU will employ pivots. So you have to be a little bit careful that the X's that are reported are coming in the order that you expect them to. Right? Because through pivoting, you may end up with slightly different X locations than expected. So always go back and check your work. and you won't have this be an issue. Lastly, in terms of factorization, I want to briefly touch on Cholesky factorization. Cholesky factorization is for symmetric matrices. If you remember, our symmetric matrices are matrices that are symmetric along that diagonal. So these values are the same as those two values are the same as those two values. Put another way, our symmetric matrices are places where A equals A transpose A. We end up being able to decompose this matrix through LU factorization as saying A equals U transform times U. We can very rapidly find that U matrix, and therefore our L matrix, using these two equations. I'm not going to go through this because it's just trudging through a lot of algebra, but I will note how one would do that. If you notice, each of these elements in U have two components to represent the row and the column that we're working in. If we're looking at a diagonal matrix element indicated by this II, it's relatively straightforward. We take the square root of the AII value, so the value of the original A, minus the summation from k equals 1 to I minus 1 of UKI squared. So everything essentially that has come before, summed up, squared, and then taking that square root. The book has a long example of actually working out this math. The off-diagonal elements are given here. It's a little bit more complicated. Instead of taking a square root, we have this equation where each row and each row I and each j are this division, where it's aij minus the sum from k equals 1 to I minus 1 of uki. So this is that k is what the summation is working over. That I is the row that I'm working on, times ukj, where k once again is that sum iteration, and j is the column that I'm working on, all over uii. Right? So this is going to be for as long as j is equal to I plus 1 to n. Right? So you'll get a chance to work on this in homework and through the book problems. I now want to transition to Chapter 11. In Chapter 11, we're going to learn about matrix inversion and how we can use this to sort of assess how accurate our results can be. But we're going to use a lot of the same ideas and actually use LU factorization in order to find our matrix inverse. Remember that we said a matrix inverse is the matrix that when I multiply it by itself comes out with the identity matrix. So we can say A times A negative 1 is equal to I, or A negative 1A equals I. We can solve for the inverse matrix by solving for in a column by column fashion. In essence, we're going to take our matrix A, take a set of x's that we're going to solve for, and solve for each row or each column of the identity matrix at a time. So if we had a 3 by 3 matrix, we would solve first for, say, this x1 vector, that's 1, 0, 0. Then this x2 vector, which is 0, 1, 0. And that third vector, 0, 0, 1. Right, if I put all three of these vectors together, they're the identity matrix of 1, 0, 0, 0, 1, 0, 0, 0, 1. Right? So we're going to do this. This is called a column by column approach. Where LU factorization is going to come in is we can solve for the LU factor, which will give us a quick and easy way to solve for different x's as I change my b's. Right? So I only have to do the elimination piece once for that A, and then I can relatively rapidly calculate the A component or the X components to that inverse matrix. So the idea, we're going to do LU factorization, solve for x1, 2, and 3, and then collate or stick together our x's into that to form that inverse matrix. Let's do an example. We're going to find what we want to find what the inverse matrix is of A. If you remember, this is the same matrix that we solved for earlier in the lesson. We're going to do this through the 3 steps. We're going to do LU factorization, solve for x1, x2, x3, and then collate the x's into the inverse A formula. Using LU factorization from earlier in the class, we have our U matrix that looks like this, and the L matrix that looks like this. Just pulling those answers forward from earlier in the class. Right. So now we're ready for step 2, which is going to be solving for the x1s using our L's and U's. I've rewritten U and L up here just as a reference. So remember, when solving matrices using LU factorization, we first take the L to get, we first take L and B and then do forward elimination to get D, and then we use D in combination with U and back substitution to get X. So let's do this out. So here I've written, I've copied down our L's. For x1, we have, I've got the D's that we're looking for, and then since we're looking for x1, we have that 1 in the first element, and then everywhere else zeros. Using forward elimination, we can say that D is equal to that first one, so 1 times D1 is 1, so then our D that first D is a 1. I can now use that first D, so 0.033333 times D1 plus D2 equals 0. Well, that's the negative 0.0333. And then I can use D1 and D2 to plug into that last row to find that D3 is negative 0.1009. Just solving these out by hand. Now I can take these D values in combination with our U matrix to solve for our X's. Here I've written out our U matrix. Here I have the X's, which is what I'm interested in, and then we have that D set. Now I'm going to use back substitution to calculate our X's. In this case, we have 10.0120 times x3 is equal to negative 0.1009. So this says that x3 must be equal to negative 0.1009 over 10.012. When we do that math out, this is negative 0.01008. So let me clear that up just a little bit. 008. Okay, then I can use the x3 that I've solved for to solve this equation. So we have 7.00333 times x2 minus 7.0033 x2 minus 0.29333 times negative 0.010808, and that's all equal to negative 0.0333. Solve this out, we find that x2 is negative 0.00518, and then we can do the same thing for that top x1, which is 0.33249. We've solved our x's. All right, so now we know that first column in our inverse matrix. All I've done is I've taken the result from this x and I put them in that first column. For the second step, we want to find the second column of inverse A. So we're going to do the same thing. We're going to solve for our d's using L and B, and then solve for x's using U and D. In this case, our B is going to be 0, 1, 0 because we're interested in finding x2. So this is B2. It's going to be used for, it's the only element that's 1, everything else is 0. We can go in and use this for the second column of our inverse A matrix. I can solve for D using forward substitution, and then we can use back substitution using these d's, and when I do this I end up getting 0.00494, 0.1429, and 0.00271. I suggest that you go through and check yourself to make sure that you understood what happened from the previous slide using this as an example, as a training exercise. Now that we have x2, I can go in, I can use this this vector. I take these elements, they now go into that second column. I'm now close to solving for my A slot, my inverse A matrix. And then finally, we can do the exact same thing for case B. In this case, when we solve for x3, I get 0.006798 and 0.004183, and then finally 0.09988. Because that should be vertical. And now I'm ready to collate everything into my A matrix. So I just take all of the pieces that I've calculated over this course. So the information from a x1 set, the x2 set, and then finally the x3 set. This is our final inverse matrix. All right. So once again, when I take this matrix and I multiply it by A, or take A and multiply it by this A vector, A inverse, we should get the identity matrix. Once again, go in and practice your matrix multiplication by checking it for yourself, and you'll find that it does in fact equal the identity matrix. Inverse matrices have a wide variety of uses beyond just solving for x's in simple matrix math. As we said before, that it's actually not a very fast process, right? As we've seen in solving for the inverse matrix, it requires quite a lot of steps that go far beyond what's needed for simple Gaussian elimination. So why are inverse matrices interesting? Well, it's because we can model many systems of linear equations as sets of some sort of interactions via matrix, some sort of system response, and set those equal to some sort of stimuli B. What this is going to allow us to do is rearrange this using the inverse matrix to say that some sort of response of a system is going to be equal to how the different bits of the system are interconnected, or what the interactions are, times some sort of stimulus. So we can say that x1 is going to always be equal to a11 to the inverse matrix of that element b1 plus a12 negative 1 times b2 plus a13 of the inverse matrix b3. What this is saying is each of these elements of the inverse matrix are the correlation between this variable and the stimuli, right? Similarly, the relationship between x1 and b2 is that inverse matrix. We can say that these relationships have two types of powers when we have linear equations. One, these stimuli interaction models have the power of superposition. The total response, say x1, is the addition of all the individual stimuli. Right? It's simply the addition of each of these individual pieces. We also say that we have proportionality. x1 is proportional to b1 by a set amount. I don't have b squared or square root. I have this proportionality that's given by my inverse matrix constant. Where this really comes in is through taking differences. So we can look at how b changes, or changes in b, are going to change x3. Right? So if I can, maybe I can write this out this way, that says, maybe we'll call this x3 prime is a31 negative 1 b1 prime plus a32 negative b2 prime plus a33 negative 1 b3 prime. If I want to see how x changes, or in other words, if I want to take the difference of the two, I can say that that difference is a31 negative 1 times b1 minus b1 prime plus a32 negative 1 times b2 minus b2 prime plus a33 negative 1 times b3 minus b3 prime. Or put very succinctly, my change in x is the interaction coefficient times the change in each of my stimuli. Let's see how this is going to be implemented in a real problem. Let's take an example that's relatively close to home. Most of the water that we drink in Tempe, or is available in the Phoenix area, comes from the Colorado River, through a series of 4 lakes: Lake Powell, which drains into Lake Mead, which drains into Lake Moab, which drains into Lake Havasu. As the water goes through each of these lakes, evaporation happens, changing the concentration of various salts within each of the rivers, within each of the lakes. Let's take one salt, for example, chloride. We could take a mass balance acting on each of these different lakes and arrange it in a different way, and in a way that is as set up as these series of matrices, where A represents our mass balance flows, C is the concentration of the chloride, and W is the load or total of the chlorine in each of the given lakes. Let's say that we have these sets of matrices shown here that are going to be representative for our system. And let's say we want to know what the concentration in each of the 4 lakes is, and then how we can see how we can alter the concentration in part B. We'll get to part C later in the lecture. So first, let's use matrix inversion to solve for the concentrations in each of the 4 lakes using MATLAB. We can program in that A matrix using this code as follows. Then we can put in what the load in each of the lakes are using this string of code. Then, of course, finally, we can calculate the inverse of our A, which is shown here. Then we can solve the concentration by taking our inverse of the A matrix, so our inverse of that stimuli matrix times that load to find the concentration at every single lake. Now we can see how we can change the concentration of Lake Havasu by changing. Now we're going to see how we can change the concentration of chloride in Lake Havasu by changing the load in Lake Powell. So that W vector, that's associated with Lake Powell, so this 750. We want to see how we need to change that W1 value, that load value, so that we can change the concentration in Lake Havasu, so that C4 value. We're going to do this using our stimuli response effects. So remember, we can say that the change in any one value, in the generic case x4, but in our case C4, changes in response to changes in that B value, or in our case, that W value. So written out in our terms, we have A times C equals W. We're interested in looking at what happens at C4. So we can say, how does our C4 variable change as we change that stimulus respect, so that those W values. And we're really only interested in changing what's happening in Lake Powell, right? Because all of those other cascade flows are already sort of fixed by what's happening in Lake Powell. So we're really not interested in what's going to happen to the other loads. Therefore, I can simplify this equation, or the stimuli response set, to say, what's going to happen? We can ask the question, what's going to happen at C4? How does C4 change as what happens in Lake Powell changes, as W1 changes? And what this math will tell us is it's all dependent on this interaction coefficient. So the A41 value of the inverse matrix. So really, what we want to know is what delta W1 is needed to get a desired C4 change. So we can rearrange this to get our final equation that's going to tell us our interactions. So the W4, so the load change that we need is going to be equal to our change in C4 over that interaction term. Okay. So let me now, I've taken that equation, I've brought that forward. We can write out our inverse matrix form, and we can write out what our different concentrations were. This is just bringing all those effects forward. So we can now start plugging things in. So we can say that the change in W1 needs to be the change in C4. So we can't just plug in 100. We need to see what the change in that is. So that's 100.2373 minus, so what it was, to be what we want it to be, say 75, over our interaction term. And that interaction term is A41. So I can go to my inverse matrix table and look up my A41 vector, which is 0.848. I can do out the math, and I find that my delta W is equal to 297.725. In other words, the change in that lake value, in that lake load, needs to be almost 300. That's how much we have to reduce that load in order to reduce this total concentration. So W1 is not equal now to 297, but rather W1 is equal to the original W, which was 750 minus 297. So this is will give us the value of 453. So we need the load to be in Lake Powell beneath 453 if we're interested in getting the concentration in Lake Havasu down to only 75. The last thing that I want to talk about is error analysis and system conditions. The last thing I want to talk about is error analysis and system conditioning. If you remember back to when we first started talking about linear algebra, we said that we can have round-off effects due to how many elements or how many digits of precision we're measuring our numbers out to. And this can have various effects depending on how similar the equations are. Remember, we said that when we have equations or lines that sort of look like that, that are very different from each other, we can get very nice solutions. But if I have lines that are run very parallel or almost parallel to each other, we can have lots of error from those small differences in precision. So this is going to be the error that's going to come through a system. So one way to analyze this would be to using the matrix coefficients. So we could take our coefficients of A so that the largest element in each row is 1. So essentially normalize each row. Then we could take that normalized matrix, invert it, and see if there's any elements that are several orders of magnitude greater than 1. In doing this, we can measure large differences in behavior, and in the inverse matrix, so that means very small differences in behavior in the original matrix, and therefore a very ill-conditioned system. We could do this another way by taking the inverse matrix and multiplying it by the original coefficient matrix and assess how close that inverse is to unity. Remember, it should be exactly unity if we had an infinite number of digits. But if we don't have an infinite number of digits, we may have small errors that could add up. If we're very close to the identity matrix, we're well conditioned. If not, the matrix is ill conditioned and we can have error. The last sort of way to do this using the inverse matrix is to invert the inverted matrix and see how close the original matrix is to the inverse of the inverse. So we can see how close the inverse of the inverse is. Is it approximately equal to A? If it's not, we have an ill-conditioned system. And so while this is conceptually satisfying, it's not very mathematically satisfying. We want to have a concrete number. So how can we do that? Well, we can do this through norms. A norm is a value of a function that provides a measure of the size or the length of a multi-component system. This is essentially taking our whole size of our matrix and squishing it down to a single number that's going to represent that whole set of numbers. So the question is, how are we going to think about this? The easiest, so the norms that you may be sort of associated with it are, that you may already be familiar with, are vector norms. So this comes across, or most commonly shown in terms of, say, a Euclidean distance. The definition of our norm, which is going to be written this way as these two upward arrows, is 1 divided by p, where p is going to be the order of the norm, of the sum of the elements in that vector. So our P1 norm, which is very important, is just the summation of the absolute value of each individual case. So essentially take every single element in that vector, take the absolute value, and sum them up. The one that I mentioned earlier, our P2 norm or Euclidean norm, we can think of as length. If you remember, when we look at a triangle, so if we have x and y, right, we can think of this length as pieces over a distance. And so we can call this second p equals 2 norm, or Euclidean norm, is the square root. So because p is 2, so p equals 1 over 2 is 1/2, the square root of the sum of the matrix elements squared. And then we can have our infinite norm, or maximum magnitude norm, where we just look for the maximum value in that vector. So what's the absolute value of the biggest number in that vector? Things get a little bit more confusing when we have matrices because we have multiple rows and elements. The first norm is sort of like that, like the L1 norm. So this is called the column sum norm. In essence, I'm going to look through my, this matrix. I'm going to sum up each element in each column, and then I look for which one is max. Right? So once again, we're just going to look for the biggest number, but we're going to take the sum of each column. The next and often used one is called the Frobenius norm, which looks a little bit like a Euclidean norm. Here I go through each element in my matrix. Go through each element, I square it, I sum them all up, and then I take that square root. So think of it like the Euclidean norm. I'm squaring every element and then taking the square root. Then we also have the row sum norm, which is very much like the column sum norm, but this time I'm summing each row and then taking the max going downwards. We also have the spectral norm, where we take the square root of this U max. In this case, U max is the largest eigenvalue of A transpose A. And so we take the A transpose, multiply it by A, we take the eigenvalue, which we're not going to get into calculating, but MATLAB can do it for you, and then you take the largest of those eigenvalues that come through. Now that we've talked a little about norms, we can talk about conditioning numbers and how we can use that to assess error. The conditioning number of a matrix is defined as the norm of the matrix times the norm of its inverse. So we can find the norm, and we can use various different types of norms, and then we can take the norm of the inverse of that matrix. So it's a little complex because we now have to not only figure out what the norm of a number is, but we also need that inverse, which requires LU factorization and everything we talked about at the beginning. Condition number is useful because we can relate the relative error in the norm of the computed solution to the error of the original matrix A. To put it another way, if I know how many digits I'm calculating in A, I sort of know what that delta A is. If I know what the delta A is, I know the maximum error in delta X, or I know the maximum error in X, or in other words, delta X. So boiling all this down, we can say that if I know T digits of matrix A, my solution X is only valid to T minus log 10 times the log 10 of the condition matrix, of the condition number of A. MATLAB has several built-in functions that are going to help us solve these problems. This includes both norms and the condition number. If I type in norm and then x comma p, I can figure out what the MATLAB will compute for me the norm of x to any number we want. So remember, if I put in 2, that would either give us the Euclidean norm or the Frobenius norm. I could put in different values of p. I could put in the infinite to get that max value, or Fro for Frobenius to get that Frobenius norm. Once again, that's a little bit double standard. And we can do the exact same thing for a matrix. MATLAB will do the same thing. Then the last thing, we can get the condition number using cond. Once again, MATLAB will be able to tell whether it's a vector or a matrix and behave accordingly. With this in hand, I want to go back to the Lake Mead problem and look at the error we would have in our solution. So we're going to use the column sum norm to compute our condition number and how many digits we can trust and how many digits we wouldn't trust. So the first step is to normalize each value to a sum of 1 so that we can take the condition number. What I've gone through and done is taken the largest number in each row by magnitude and set it equal to 1. So that first value is 1. We can then see we have 1, negative, 0.9, etc. for each row. I then take the sum of each column. So 1 plus 1 is 2, negative 0.9, negative 0.98 gives us negative 1.902, etc. So then our column sum norm is 2. Now I can use the inverse of A to figure out, now I can calculate the inverse of A. So if you remember, we have our A, and then we can use MATLAB to calculate our inverse. Now we can calculate the our column sum norm. In this case, it's 4.314, summing each of the individual columns. And we can now calculate the condition number. Remembering that the condition number is my column sum norm of A times the column sum norm of inverse A. So of A was 2, and of inverse A was 4.3. This gives me a condition number of 8.635. So then we're ready to find out our last step, how many digits are suspect, or how many digits do we not trust. We take the error, we have our log 10. Our condition number, we take the base log 10 of that 8.635. When I do that, I find that I have 0.93. This means I'm suspect of less than 1 digit in my original matrix. And that's what I wanted to cover today. So in review, we've talked about how we can use Gaussian elimination to get LU factorization. We've touched on the Joukowski method. We've used these methods to solve inverse matrices, and then talked about stimulus response characteristics. Then lastly, we talked about matrix norms, conditioning numbers, and how we can estimate the precision of our solution. All right, see you in class.